Hello, in this video we are going to go over the solution of the problem 253 meeting rooms second. The description of the problem is given an array of meeting time intervals consisting of start and end times, for example S1, E1, S2, E2. Find the minimum number of conference rooms required. For example, if I have three intervals 0 to 30, 5 to 10, and 15 to 20. When I have the first interval 0 to 30, I allocate one room. Then I come to the second one and I say, okay, do I need a new room or can I use the room number one? But because the first meeting is still going on, I have to allocate the second room. And when I come to the third interval, so the beginning of that is 15, and you can see for the second meeting, the end is 10. So the second meeting is over, so I can allocate the room number 2 to the third interval. So at most, I only need 2 rooms for these 3 intervals. Now imagine that I have 7 intervals, 1 to 10, 2 to 7, 3 to 19, 8 to 12, 10 to 20, and 11 to 30. And all of them are sorted based on the beginning time. So 1, 2, 3, 8, 10, 11. And now I'm going to find out how many meeting rooms I need. So let's go and see that. So for example, this is my first meeting from 1 to 10, and I need one room for that. And then for the second interval, so that is from 2 to 7, I need another, and I need 2 rooms. So the summation of the rooms is 2. Then I go for the third one. For the third one, third one is from 3 to 19. So I need 3 rooms. Now let's go for the other one. So now you see for the other one, 8 to 12. So the beginning of this meeting is actually larger than this meeting. It means that the second meeting is over. So I can allocate that room to that. So in fact, we are checking the beginning of each meeting to the end of already started active meetings. So here I saw that I'm comparing the beginning of this fourth interval to all of the endings. So the ending of 1 is 10, ending of second is 7, and ending of the third is 19. And only one of them, which is the minimum one, is number 7, and that is smaller than beginning of it, which is 8. So in that case, I can delete this group. I can delete this individual interval and say, okay, I only need 3 rooms because 3 arrows are left. And then I continue now again. So I have the beginning of this, which is 10, and I compare that to the existing intervals. And the existing intervals are this one, and this one. And you see the first interval ends, and I can actually allocate the first room because that is ending at 10 and beginning at 10, so that is possible. So I can delete this one, the first interval, and allocate the room to the third one and the last interval. So for the last interval, the beginning of that I'm comparing to the end of the beginning arrows, so to 20, 12, and 19, and all of them are larger than the beginning, so I need another room. So I need 4 rooms. If you look at how we solve this problem, you can see, for example, here when I'm trying to compare the beginning of the fourth arrow, the fifth arrow, sorry, to the first arrow. So you see, I'm looking for the minimum of the existing intervals. So instead of going to all of these arrows, instead of going to this arrow 12 and 19 and 10, if I have a min heap that could tell me what is the minimum, that data structure of priority queue min heap is useful here. So then I can save time. Instead of looping through all of these arrows and checking all of them, I can easily check to the minimum of them. And that is what we are going to do in the next slide. Okay, now we are going to use min heap. So we are going to include all of the ending times in our min heap. So now let's go forward. So I have the first interval 1 to 10, and I have a one node 10 added, and the number of room is the size of the min heap, which is 1. Now let's go for the second one. So I have the interval 2, 7, and now I'm comparing the beginning of this, which is 2, to 10. 2 is smaller than 10. It means that I'm going to add the number 7, which is the ending of that interval, to my heap. So add that, so that will be replaced, because this is min heap when you add something. So first I add it here, and then that will be compared, and that goes up, and 7 is on the top right now. So, and the size of that is the size of my rows, which is 2. I go forward for the third one, and we can see, okay, for the third one, that's the same thing. So again, beginning of the third one to these two, which is 7 and 10. So, but 3 is still less than 7. So I'm not going to compare to both of them. You see, I only compare with 7. That's where we are saving time. So I'm going to add 19 because we are adding the ending of that. Then, and the size is actually, size of it is 3, so we need 3 rows. Then we go for the next one, 8 to 12, and here is actually interesting. 8 is greater than this min heap, so it means that I can get rid of this. So I'm gonna delete this node and add 12 to the tree. So I deleted that and I added 12. And if you do that in a how you insert and delete a node from a tree, you can, at the end you have this tree, which is size of that is still 3. Okay, let's look at the next interval, interval 10, 20, and I'm comparing the beginning of that, which is 10, to the min heap, which is that is equals to that. It means that I need to delete this 10 here and insert 20 to the tree. So you can see I deleted 10, 12 shifted up as the minimum, and when we added 20, that comes here. And the size of that is 3, so that's the number of room required. And the last one, 11, 30, so 11 should be compared to 12. And that is smaller, so it means that I need to add its ending to the min heap. So I add that, and the size of that, which is 4, is the minimum required rows. So in this way, whenever we are comparing the beginning of each interval to all of the existing ending of the other interval, so we don't have to go through a loop and compare all of them. So we just compare to the what we delete from the min heap, which is the minimum value of those beginnings. So in that way, we are saving a lot of times. Next, we are going to see how to implement that in Python. Okay, now we can go over the code to see how we can implement that. So the first thing in Python that when we are going to use the priority queues, is that I want to have a min heap, so I import heap queue, and I need to use 2 functions. One is heap push, whenever I want to insert a node to the heap, and I also need to use another function called heap pop. That's when we are removing the root, which is our minimum of the nodes in a minute. And that is for this function. And also this function requires a list. We call that rooms here. And this list, the first element in this list, room 0, is going to be the minimum value. That is the value of the min heap. value of the node in here. So that is the other one that we need. And so let's imagine that I have these intervals. So as we remember, so we had these intervals and we explained that those are sorted. For this one, if they are not sorted, we can just easily sort them at the beginning. So we sort them based on the beginning of the intervals. Okay. Then what I do is that I come, that is sorted. So I come and say in the sorted intervals. So for the 0, 1, it's gonna be 0, 1 is a 0, and this is 1, 10 is 0, because that's the first element, and then 1 is 10, and that is added to the rooms, like here. You see this purple? No, that's the one. So we add that, and then we go for a for loop, and we start intervals from 1 to the end of the intervals, which is going to be 2, 2, 7, 3, 19, 8, 12, 10, 20, and 11, 13. No matter of the condition, we saw that in the solution that we are always adding the ending of that interval to the tree. So here, so I1 is the ending of that interval, because I is our interval, different intervals that we have. For example, it could be 2, 7, 3, 19, 8, 12, and always we are adding, no matter of the conditions, we are adding the ending of that to the tree. And the function we use, as we said, is heap push. But for conditions like here 8, 7, or comparing 8 greater than 7 or 10 greater or equal to 10, so in those conditions, when the beginning within the beginning of the interval, so for example I0, for I0, when I0 is greater or equals to rooms 0, rooms is the one, as we said, is going to room 0 is going to return the minimum nodes, the root. So that is exactly like the things that we see here. Okay, so in that condition, we are going to remove the root, and when we use the function heap pop, so heap pop is going to remove the roots, and the return of the function, as we saw that the size of the min heap is the minimum number of rows. So we just need to return the length of the list rooms. So that is going to be the required number of rows, because that is the number of nodes in our tree. So let's run this. We can see the solution is 4. That's the minimum required number of rooms. And let's look at the time and space complexity. First of all, we sorted the intervals. So here, at best, we are going to get n log n. So that is for optimum sorting. Then what we did is that we have here one heap pop. So for this one, so we are deleting the root. And as we know, the time complexity of that for a tree is log n. Also, here we have heap push. And heap push, the time complexity is a number between 1 to log n. But as we consider the worst case scenario always, so we say that is log n. So we have log n here, 2 log n, and we are in a loop, and so n times, so that's going to be n log n, or 2n log n, or n log n, plus n log n here, so the time complexity remains n log n. So the time complexity is n log n. Also, imagine in a case that we are adding all of these for the space complexity. Imagine the scenario that we're adding all of these nodes to our list of rooms. So imagine that we have a situation that none of them got deleted. So, and the rooms is increasing and increasing and to the end. So because of that, So we might end up having, in a worst case scenario, to have n elements in a in the list rooms. So in that, because of that, the space complexity is order of n. So again, so we saw that how to use the function heap_q. We just need two functions of that. We know that the rooms is a function in Python that is a list, that the beginning of that, the first element of that is the minimum value. And we saw that how we can consider the time complexity and space complexity, and that's pretty much everything about solution of this problem. And thank you so much for watching this video.